Hello and welcome to this video series on microwave tubes. In this video series, we will discuss about different microwave tubes such as two cavity klystron, multi cavity klystron, reflex klystron, traveling wave tube, and magnetron. So for our upcoming videos, we will talk about all these tubes one after another. But one question arises in our mind: if we have conventional vacuum tubes such as triodes, tetrodes, and pentodes, which are already available, why we use these specially designed tubes at microwave frequency? So, in our first video tutorial, we will discuss about limitations of these conventional vacuum tubes. So, the topic of discussion is limitations of conventional vacuum tubes. So, what are these conventional vacuum tubes? Triodes, tetrodes, and pentodes. So, there are three important limitations. First limitation is lead inductance and interelectrode capacitance effects. Second limitation is transit angle transit angle effects. And third limitation is gain bandwidth gain bandwidth product limitation gain bandwidth product limitation. So we will try to see these limitations one after another. So let us start with the lead inductance and interelectrode capacitance effects. Because of this limitation, if we use conventional tubes at microwave frequency, output power is decreased rapidly due to this effect. So output power decreases rapidly because of this lead inductance and interelectrode capacitance effect. So to understand this effect, we will consider a triode circuit. So this is a triode which has got three leads: gate, cathode and plate. We have a tank circuit where R is the load resistance, L and C, which we are using here, are actually tuning elements, and we have considered lead inductance of cathode terminal only. We also know that in case of this triode, separation between gate and plate is more than that of the separation between gate and cathode. So this is important understanding. So to do the analysis and try to understand the lead inductance and interelectrode capacitance effect, as we have said, because of this, output power of the conventional vacuum tube will reduces rapidly. So we'll try to prove this with the help of equivalent circuit of this tube. So the triode we have replaced with interelectrode capacitances. So the capacitance between gate and cathode, modeled as CGK, and the capacitance between gate and plate modeled as CGP. So these are interelectrode capacitances CGK and CGP, and the lead inductance is LK. Again we have R, L and C. Current flowing through circuit we have denoted as I in. Input voltage is V in, output voltage is V0. So the only effect of interelectrode capacitances and lead inductance is being analyzed under this topic. So what we will do, we'll start our discussion and we'll prove that if or because of this effect, output power of a particular tube decreases if we increase the operational frequency. So ultimately we are going to prove that what is the input impedance for a particular tube, which is triode in our case, and we'll try to prove that since it is impedance, it has real and imaginary part. So if the real part of input impedance is varying with respect to frequency, and moreover it is inversely proportional to the frequency, so as operational frequency increases, real part of input impedance, real part of Zin reduces. Similarly, even imaginary part will also reduces, so that what will happen, as if we increase the operating frequency, input impedance real part will reduces, and very soon it will reach to the value 0, so it will short the input side of the tube, so result of that output power will reduces. So to do that, we will start with the assumptions. We have two assumptions for this discussion. First is assumption number 1 is CGP is less than CGA. CGK. So what is this assumption? We have CGP, interelectrode capacitance between gate and plate, and we have CGK, interelectrode capacitance between gate and cathode. So we assume that CGP is less than CGK because separation between gate and plate is more than gate and cathode, and we know that C is equal to epsilon A upon D. If the separation between gate and plate is more, so the capacitance between gate and plate will be smaller value. That is why we have assumed that CGP is less than CGK. Our second assumption is omega LK is less than 1 over omega CGK. So that means XL is less than XC. And why we are saying that? Because we are assuming leads are short. So with these two assumptions, we will start analyzing with respect to this equivalent circuit. So first we have to determine for its input impedance. So first we'll write for V in, then we'll write for I in. From V in and I in we can obtain admittance, which is input admittance, and then we'll take its inverse, so we'll get the input impedance, and we'll see how the input impedance varies with respect to frequency, so that we will understand the limitation of lead inductance and interelectrode capacitance. So for V in, so you can see here V in is actually VG plus VK. So I can write V in is equal to VG plus VK. What is VK? For this diagram, what is VK? V is equal to I into R. So I is GM into VG and R is XL. XL is J omega L. So J omega LK GM. So VK, that is actually equal to I into R. So current flowing through that inductance is GM VG into R is the inductive reactance, which is J omega L, and L is LK. Current flowing is GM VG. So VK will be equal to GM VG J omega LK. So I can write here V in is equal to VG plus VK is J omega LK GM VG. Now, once we have written for V in, let us write for I in. And while writing I in, we will be ignoring LK because we have second assumption, omega LK is very less than 1 over omega CGK. So now let us write for I in. For I in, ignoring LK, and assumption, what is that? Since omega LK is very less than 1 over omega CGK. So what is I in? I in is equal to, for this and ignoring LK, so V is equal to I into R, I is equal to V by R. So this I in is equal to VG by R is the capacitive reactance, which is XC, and XC is 1 over J omega C. So we'll write for this I in is equal to V G over capacitive reactance XC, and XC is equal to 1 over J omega C, and that C is for interelectrode capacitance GK, CGK. We are ignoring this. So 1 over J omega CGK. Therefore, I in would be XC is 1 over J omega CGK. Putting here, it would become J omega CGK VG. So now we have V in and we have I in. From this I in, I can write Vg is equal to I in or J omega CGK. Okay, so let us call this equation as 1. Now call equation 1 and use the value of Vg which we have obtained. So V in is equal to, so equation 1 becomes V in is equal to, equation 1 was, I will rewrite, it was Vg plus J omega Lk Gm Vg, and Vg we have obtained. So let us put this Vg here and take common Vg. So it would be 1 plus J omega Lk Gm, and using value of Vg which is I in divided by so here I will write clearly using Vg is equal to I in over J omega CGK. So this we have obtained V in. Now let us try to write for input admittance. So Y in is input admittance and it is I in over V in. So from this equation, I in over V in, so I can write I in divided by, using the value of V in, I in into 1 plus J omega Lk Gm, and that denominator J omega CGK will go to the numerator. This can be cancelled out, so Y in will be equal to J omega CGK divided by 1 plus J omega Lk Gm. So just rewrite Y in this particular fashion: J omega CGK inside the bracket 1 over 1 plus J omega Lk Gm. Now we have purposely written this equation in this particular form, and omega Lk Gm is very small quantity, so that is why we could consider this as x, and we can use binomial series such as 1 over 1 plus x is equal to, which can be also written as 1 plus x raised to minus 1 is equal to 1 minus x plus x square minus x cube, and so on. All these higher order terms can be neglected. So it can be approximated, 1 plus x inverse can be approximated as 1 minus x. So here we have 1 upon 1 plus x, so that can be written as 1 minus x. So y in, we can write, or before that, this particular term, entire term, the term 1 over 1 plus j omega lk gm is equal to, approximately equal to, minus j omega lk gm, and therefore y in is j omega cgk inside the bracket 1 minus j omega lkg. So multiply inside the bracket. So y in is equal to j omega cgk, j into j square, j square is minus 1, minus minus would become plus omega square lk cgk gm. So this is an input impedance, input admittance for the tube which we have selected, which is a triode. So now we'll try to obtain input impedance. So input impedance. We know that y in is actually equal to omega square lk cgk gm plus j omega cgk, and if we take inverse of this, that would be z in. So 1 over y in would be our input impedance. And we also like to separate input impedance into its real and imaginary part. So we'll multiply and divide by complex conjugate of this term y in, multiply and divide with the same. So z in is equal to omega square lk cgk gm minus j omega cgk. So this is complex conjugate of y in. We have multiplied in the numerator. In the denominator we have y in and multiplied by its conjugate. So by looking at the denominator, we have this denominator in a particular fashion, which is a plus b into a minus b. So a plus b into a minus b is equal to a square minus b square. Now let us continue. So this term we would like to modify So this term Zn, okay, is equal to omega square Lk Cgk Gm minus j omega Cgk divided by a plus b into a minus b. We would like to like as a square minus b square. So omega raised to 4 Lk square Cgk square Gm square. So j square is a minus 1, and this minus minus would become plus omega square Cgk square. Now let us separate the real and imaginary part. So Zn is equal to omega square Lk Cgk Gm divided by omega raised to 4 Lk square Cgk square Gm square plus omega square Cgk square minus j omega Cgk divided by omega raised to 4 Lk square Cgk square Gm square plus omega square Cgk square. Now let us take out omega square Cgk square common from the denominator. So Zn is equal to omega square Lk Cgk Gm omega square Cgk square common. So here we will have omega square Lk square Gm square plus 1. Similarly to the imaginary part, omega Cgk divided by omega square Cgk square. So omega square Lk square Gm square plus 1, right? So let us cancel out the common terms from numerator and denominator. So omega square Cgk and 1 Cgk can be cancelled out. Here also omega from 1 omega from numerator, 1 from denominator, 1 Cgk from numerator. So Cgk from numerator, 1 from denominator can be cancelled out. So remaining term or modified Zn is Gm Lk Cgk omega square Lk square Gm square, and we are neglecting this one because omega Lk is very less than 1 over omega Cgk. I mean, we have assumed this omega Lk is very less than 1 over omega Cgk. So if this quantity, total quantity, is higher, then that denominator quantity will be has to be very small. So we are ignoring this omega Cgk minus j 1 over 1 omega has cancelled with this one. So it is omega into omega square omega cube Cgk Lk square Gm square. Again we have neglected this term 1, similar to this one. Now again cancel out the common terms. So Gm will cancel with this 1 Gm, Lk can be cancelled. So finally Zin is equal to 1 over omega square Lk Cgk Gm minus j 1 over omega cube cgk lk square gm square. So this is the required expression which we were trying to obtain, and now from this expression, since this is a real part and this is an imaginary part of input impedance, we know that the input impedance real part is varying inversely with the square of the frequency, and its imaginary part varying as the third order of the frequency. So as if the operating frequency increases, input impedance becomes short and output power reduces for the given conventional vacuum tube. So how do we reduce this effect? That we will discuss related to the lead inductance and interelectrode capacitance. Lead length can be shortened. That is the first thing which we can do to reduce this effect. Lead length can be shortened and we can reduce electrode area. So by reducing an electrode area, as we know C is equal to epsilon A upon D, if we reduce this area, capacitance will reduces, that is the interelectrode capacitance. But both these solutions will result into less power handling capacity. So that is why these are not the proper solutions to reduce lead inductance and interelectrode capacitance. So we'll see the other two limitations in our upcoming video. That is all for this video. Thank you.